Assalamualaikum and hi everyone. We continue the last subchapter for analysis of beam for bending, which is a Flexural Formula. Take a look at the learning outcome. By the end of the chapter, you should be able to explain the internal moment and bending, normal stress in the beam, calculate the section properties about the natural axis of symmetrical or unsymmetrical 2D cross-section area of a beam, calculate the second moment of inertia about x-axis at the different cross-section area of a beam, apply and analyze the bending stress in the beam by using Flexural Formula at the specific locations. In this chapter, you will learn about the Flexural Formula, which is the important for you to calculate the stress in beam. So from the Flexural Formula, you will calculate the bending stress in beam. The cross-section of beam depends on the design. You will have a symmetrical beam and also the unsymmetrical beam. For the introduction, previously you have learned how to determine the shear force and bending moment at any section of the loaded beam. In future work in structural design, you will learn how to design beams capable of withstanding the effects of shear force and bending moment. As an introduction, the analysis of bending stresses that result from the application of bending moment will study. From shear force diagram, you have the maximum shear. From bending moment diagram, you will have the maximum bending. From this value, you will calculate the bending stress of the beam. Okay, there is some relationship between both. Analysis on bending stresses. When loads are applied perpendicular to the long axis of a beam, bending moment are developed inside the beam, causing it to bend. It will show the curved shape as shown in this figure. So this is your beam. When the load applied to the beam, it will bend. Okay, so your beam will bend after applying a load. It is revealed that the fibers of the beam near its top surface are shortened, while at the bottom surface are elongated. So this is your beam. When you apply the load, so your beam will bend. So it is said that the top here, this is the top of the beam, is shortened, which is it compressed, shortened due to a compression, while at the bottom it is elongated because it is due to a tension. You can take your elastic ruler and then try to bend it. Then you can see at the top of your ruler is shortened, while at the bottom is elongated. It is shortened due to a compression. It is elongated due to a tension. Cross-section of a straight beam remains plane when the beam deforms due to a bending. As a summary, material above the centroid will be in compression, with the maximum compressive stress occur at the top of the surface. The material below will be in tension, with the maximum tensile stress occur at the bottom of the surface. Along the centroid axis, it is a zero strain and zero stress due to a bending called as a natural axis. I will explain later why at natural axis it is zero. Why? And at the top here, you will have a maximum at the top and maximum at the bottom. We will take a look after this. Why? To calculate the bending stress, you have the Flexural Formula. Resultant moment of the cross-section is equal to the moment produced by the linear normal stress distribution about the natural axis. It is shown that the bending stress is inversely proportional to the moment of inertia of the cross-section with respect to its horizontal centroidal axis. by that statement, theoretically we can express that the stress, the bending stress, is equal to negative my over I, whereas the sigma here is the bending stress. M here is the maximum moment that you get from the bending moment diagram. Y here is the distance. Distance from natural axis to a point. And I is a moment of inertia. By the right hand rule, the negative is due to a compression at the top. So that's why in Flexural Formula you have the negative my over I. So you have to remember the y. This is your first y. You will meet another y after this. And also in chapter 6 you will have another y. Please remember the y here, it is a distance from natural axis to a point. There are some guidelines to calculate the bending stress. Determine the maximum bending moment on the beam. So you will determine the maximum bending moment by bending moment diagram. And then locate the centroid of the cross section of the beam. From the centroid you will get the natural axis of the beam. Compute the moment of inertia of the cross section with respect to its natural axis. Then you calculate the moment of inertia. After that, compute the distance from centroid, which is from natural axis to the point. And then compute the bending stress by using the Flexural Formula, which is the bending stress is equal to negative my over I. There are some conditions for applying the Flexural Formula to the beams. First, the beam must be straight or nearly straight. The cross-section of beam must be uniform. All loads and support reactions must act perpendicular to the axis of the beam. The beam must not twist while the loads are being applied. The beam must not be relatively long and narrow in proportion to its depth. The material must be homogeneous and also isotropic. The stress resulting from the load must not exceed the proportional limits of the materials. No part of beam may fail from instability, which is a buckling or crippling. The section where the stress is to be computed must not be close to the point of the application of the point load. This is an example of the beam. This is the symmetrical cross-section. What does it mean by symmetrical? For example, when you fold, you will get the same shape. Okay, this is symmetrical in y and x axis. Symmetrical in y and x axis. Same goes to this one. It is symmetrical, this is symmetrical, and this is also symmetrical. Means that when you fold, you will get the same shape. This one is unsymmetrical. So for example, this beam is not symmetrical in x and y axis. This one also is not symmetrical in y and x axis. And this beam is not fulfill the condition of number 5, 8 and also number 9. After you calculate the bending stress of the beam, you have to draw the stress distribution diagram. As mentioned earlier, a beam will deform under the influence of a bending moment. The segment assumes the characteristic bend shape as the upper are shortened while the lower are elongates. The natural axis remains 0, coincident with the centroidal axis of the beam. This is an example of the stress distribution diagram. To present the bending stress distribution diagram, we can express it by definition of bending stress at the specific point located as below. As mentioned before in the statement, at the top is a maximum. This is the top of the beam is a maximum bending stress. At the bottom also the maximum bending stress. And at natural axis, the bending stress is 0. Okay, so you will get this type of stress distribution diagram, but the value is depends on your shape and also on your maximum moment value from the bending moment diagram. In general, stress distribution diagram will vary linear with the distance of the natural axis. For example, if the natural axis is in the middle, so you will have this type of stress distribution diagram. For symmetrical, for unsymmetrical, so maybe the location of natural axis is not in the center, so you need to locate where is your natural axis, and then you can draw the stress distribution diagram. So we try this example. Okay, take a look at example 5.6. Analyze the simply supported beam in the figure to calculate the maximum bending moment in the beam. If the x-axis rectangular beam is 150 times 50 mm, determine the maximum bending stress of the beam. Okay, so if you refer back to example 5.1 in page 89, we already analyzed this beam. We already get the maximum moment. Okay, so refer back to page 99. Refer to page 99. So we already analyzed the beam, and then from bending moment diagram, you get the maximum moment is equal to 625 Newton meter. And then the next question asks you to calculate the maximum bending stress. You know that the maximum bending stress is occurred at the top and also occurred at the bottom of the beam cross section. This is the beam cross section. When you cut the beam, then you can see from front view that the beam is in a rectangular shape. Then you can calculate the maximum bending stress. So first step, you have to calculate the support reaction, and then after that you have to draw the shear force and bending moment diagram, and then you identify the maximum moment. And the next steps is for you to identify or for you to calculate the moment of inertia. How to calculate the moment of inertia for this one? You have this rectangular shape which is 50 mm times 150 mm. You know that I, moment of inertia, is equal to pH cube over 12. So 50 is a P, H is a 150. I convert it into meter. B 0.05 times H 0.15 cube divided by 12 is equal to 1.406 times 10 negative 5 meter 4. And after that, you have to identify the natural axis. Sometimes you have to calculate, sometimes you have to identify. This is the symmetrical. So how to get the symmetrical? How to calculate the natural axis for symmetrical? So sometimes I will do as a y bar. The symmetrical is 150 divided by 2. Symmetrical. Okay. Then you get the natural axis is equal to 75 mm. And then here you draw where is your natural axis. Okay. It is symmetrical from the bottom. 75 mm. This is your natural axis, so you have to draw where is your natural axis. And then by using Flexural Formula, then you can calculate the maximum bending stress. We start at the top. So for top, your Freebody diagram, this is your natural axis. So your y is from natural axis to the point. This is your y. Then you already identify the y, then you can calculate the bending stress at the top is equal to negative m, which is 625 times y, 0.075 divided by I, which is 1.406 times 10 negative 5. It is equal to negative 3.334 megapascal. Freebody diagram here is very important for you to identify your y value. This is very important. Okay, now you already identified the bending stress at the top. Now we do at the bottom. Bending stress at the bottom. Draw the Freebody diagram. This is your natural axis. This is your distance. And your y is from natural axis to a point. So this is your y from bottom. This is for your top. Okay, now you already identify the y, so we can calculate the stress at the bottom. Is equal to negative 625. Because it is below natural axis, then you have to put the negative. It's below 0.075 divided by 1.406 times 10 negative 5 is equal to 3.334 megapascal. Now you have the maximum stress. One is negative because it is at the top. At the top, as in the lecture note, at the top, the beam will tend to, this is your beam, and then this is your load. After you apply the load, the beam tend to bend. Okay, at the top, it is shortened due to a compression. So that's why here is a negative. And at the bottom, it is elongates due to a tension. So that's why here is a positive. How about at the natural axis? So if you calculate the bending stress at natural axis, you don't have any y value, because y value is a distance from natural axis to a point. If you calculate the bending stress at natural axis, then the y is from natural axis to natural axis, then the y value will be 0. So that's why it states that at natural axis, the bending stress is equal to 0. Understand? Now we draw the stress distribution diagram. So locate your natural axis. So you have 3 points at the top, natural axis, and also at the bottom. draw a line here, and then this is stress and PA. So at the top you have this value, same as a normal axis. This is negative and this one is a positive. You have at the top is negative 3.334, at natural axis is equal to 0, and at the bottom you have 3.334. At the top is this negative. Then you connect the line. So you will have the stress distribution diagram. Okay, we continue to page 104. For this one, read the question. The simply supported beam has the cross-section area as shown in figure. Determine the maximum bending stress in the beam and draw the stress distribution diagram of the cross-section at the specific point as shown. So this is a beam, this is a pin, and this is a roller. This is a beam cross-section. When you cut this beam, you have this type of cross-section. Then you have to calculate the stress distribution diagram. So for this one, this is the I-beam. For I-beam, you can use a table to calculate the moment of inertia. So you construct the table and divide this one into 3 shapes. This is shape number 1, number 2, and this is number 3. Then you draw the table. You construct the table. Section Y, so you make another Y. Area, times Y, area times Y square, and the last one, the I for each section. So you have section 1, section 2, and section 3. Construct a table and then do the summation. For AY, for A, AY square, AY, and I will explain to you what is this Y. The Y here is a distance from reference line to the center of the section or area. Okay, for example, you would like to analyze the first segment or section. Okay, as I mentioned, I divide into 3 sections. This is section 1, section 2, and section 3. Reference line, if it is mentioned in the diagram, so you take reference line at the bottom. This is your reference line. Okay, and then you have to determine your Y value. For section 1 here, the Y is a distance from reference line to the center of the section. So from reference line to the center of section 1 here. This is your Y for section number 1. And then for number 2, from reference line to the center of section number 2. And for y number 3 is from the reference line to the center of section number 3. Okay, this is your y. And then after you calculate an I, and then to calculate an I, you have to use the formula. Okay, after you get the value here, what is here, what is here, what is here, then you can calculate I. So I here, you have to use this formula. I is equal to AY square, which is you get from this value, plus summation I, you get from this value, minus summation A from this value, times y bar square. Y bar here is a natural axis. Since this is symmetrical, then easily you can calculate the natural axis, which is 340 divided by 2. Then you will get your natural axis 170 mm. Or you can calculate natural axis from the table. Okay, you have the table, or natural axis is equal to summation of AY divided by summation A. Summation of AY, so you take from here, divide by summation A, then you take this value, then you will get the same natural axis. Okay, and then you proceed to calculate the stress. The bending stress at the top, bending stress at the bottom, and at the natural axis, and also at point B, as mentioned here in the figure. Let's see, it's a natural axis. Okay, this one I leave it to you. You have to do by your own. Okay, I would like to show you this example. Determine the maximum moment by using graphical method. Determine the bending stress at point A, B, C, and natural axis of the cross-section beam as shown. Thus, draw the stress distribution diagram. Take the reference line at the top. So here reference line is given, which is you have to take from the top. If it is not mentioned, then you have to take reference line at the bottom. Okay. So first, again, you have to draw the Freebody diagram and then calculate the support reactions. After that, you have to draw shear force and bending moment diagram by using a graphical method. And then when you draw the shear force and bending moment diagram, and then from bending moment diagram that you do, you will get the maximum moment is equal to 15 kilonewton meter. So please draw and check your answer with my answer. Make sure it is same, or else you have to redraw and recalculate your support reactions. Please do, because in question, usually if you look at the, so this is an example of midterm exam question. First or foremost, you have to calculate the reaction and then draw the shear force diagram, and then you have to identify the maximum. And after that, this is the final exam question. Same, you have to calculate the support reaction and then draw the shear force bending moment diagram. After that, you have to calculate the bending stress. So you need the support reaction value and you need to draw the shear force and bending moment diagram in order for you to answer question C and question D. Okay, question C, you need maximum moment while question D that we teach by Mr. Kalimi later in chapter 6, you need the maximum shear from shear force diagram. This one is from bending moment diagram. So by hook or by crook, you need to know how to calculate the separation, and you need to know how to draw the shear force and bending moment diagram. Okay. So I skipped that step. So I assume that every one of you know how to draw the bending moment diagram. We calculate the moment of inertia. First, you just we redraw back the diagram to 2D shape. This is point A, this is point C, and this is B. Okay, you put all the dimensions, and then this is symmetrical or unsymmetrical? No, this is unsymmetrical. This is unsymmetrical. Then for unsymmetrical cross section, you need to construct the table. Okay, so divide this one into two sections. This is section 1 and this is section 2. Okay, so you construct the table, and then you determine what is the y value for 1, and then what is the value for section 2, and then the summation. The rest you calculate. I just gave you the summation. I do it in meter. 4.185 times 10 negative 3. 1.096 times 10 negative 3. 6.181 times 10 negative 5. Okay, you have to do by your own, and then you check your calculation with mine. And then this is unsymmetrical. Then for you to calculate the natural axis, so you need a formula. Summation AY divided by summation A. So we already calculated here. Then summation AY is equal to 4.185 times 10 negative 3 divided by 0.018 is equal to 0.2325 meter. And then number 2, you have to calculate I. I is equal to summation AY square plus summation I minus summation A times y bar square. So AY square already calculated, 1.096 times 10 negative 3 plus summation I 6.818 times 10 negative 5 minus summation A, which is 0.018, and then y bar 0.2325 square. This one is equal to 1.912 times 10 negative 4 meter 4. Okay, so please calculate and recheck my value. Make sure it is same. And then we can start calculate. So you have to calculate the bending stress at point A, point C, and also point B. Make sure when you calculate here, you take reference line at the top. Okay, so y here is the distance from reference line to the center of area. Now you have all the values. Okay, we start to calculate the bending stress at point A. Draw the Freebody diagram. This is your natural axis. Marks where is your natural axis. Okay, 0.3235 from top. So this is your natural axis. The distance here 232.5 mm. Then identify your y. Y is a distance from natural axis to a point. Then this is your point A. So this is your y for A. Okay. Then you have your y. You have your natural axis. You have your I. Then you can calculate the bending stress at point A is equal to negative my over I, whilst m's already calculated, which is 15 kilonewton meter. Then negative 15 times 10 power of 3 times the distance of y is equal to 0.2325 divided by I, 1.2 times 10 negative 4. This one is equal to what? You have to calculate in megapascal. Then same goes to point B. Draw the Freebody diagrams. So the distance and then your y is from natural axis to a point. This is your YB. And then calculate the bending stress at point B. Negative my over I. 15 times 10 power of 3, because it is below natural axis, then it's negative 0.0975 divided by I, 1.912 times 10 negative 4. Then you will get the bending stress for point B. Then proceed with point C. Again, draw the Freebody diagram. If you didn't draw the Freebody diagram, then you didn't know where to take the y value. So this is your C. Draw where is your natural axis. So point C, natural axis to a point here. So this is YC. So what is your YC value? You have to calculate. Negative 15 times 10 power of 3 times negative YC, because it's below, divided by moment of inertia. Then you will get your YC. And then to draw the bending stress diagram, you need the natural axis, because the equation also asks you to calculate at natural axis. Then you know your natural axis point, you don't have any y, then stress at natural axis is equal to 0. And then after that, you draw the bending stress diagram. then you have to plot. Okay, so you have to complete this one until you get the stress distribution diagram.